Welcome everyone. So in this lecture, we're going to continue with diode AC analysis. So let's solve another problem. So in that problem, so this is our circuit configuration. So we have a R1 resistance with 5K, and then we have R2 resistance 2K, and a diode D1 is connected parallel to R2. So which means we have a parallel combinations. So we have already seen diode connected parallel to a resistor in diode DC analysis. So we're going to analyze a diode circuit for AC signal where the diode is connected parallel to a resistor. And V node is the output wave shape and Vi is the input wave shape which is applied between these 2 points. Okay. So also notice the orientation of the diode D1 is upward direction. So that means if you keep the signal to my left, so it is in anti-clockwise direction. So in that case as well, the steps we are going to follow are very similar to the steps that we followed for diode AC analysis, for half wave rectifier, and for full wave rectifier. So that means we're going to apply the same steps. First of all, we're going to determine the transition state voltage for that circuit. So if this is our input signal, which means our amplitude of the signal is 10 volt. So that means the sine wave, the input signal fluctuates between 10 volt to minus 10 volt. So first thing, step one would be to determine determine transition state voltage. Now we already know at transition, voltage across the diode for silicon diode is 0.7 volt, but the current through the diode is 0. So this way we are going to find out the value of Vi when it is fluctuating between 10 volt to minus 10 volt. At what value of Vi we are going to have our transition. For that, let's redraw the circuit. So let's redraw the circuit considering that the diode is going through transition. So first of all, since the diode is going through transition, we're going to replace the diode. Okay. So let's say our Vi is positive. Let's say where Vi is positive, where R1 is equal to 5K and 0.7 volt and R2 is equal to 2K, which is our V naught. All right. Now, since the diode is going through transition, so that means the current in this branch I is equal to 0. So at transition we know Vd is equal to 0.7 and Id is equal to 0. So I is equal to 0. So since I is equal to 0, let's say the current flowing in this I1 and in this branch is I2. Now if we apply KCL at this point, so we find I1 plus I equals to I2. Then we already know I is equal to 0. So that means I1 equals to I2. So which I can say that R1 and R2 are R1 and R2 are in series. So I have found out that R1 and R2 are in series because the same current is flowing. I1 and I2 are same, the same current is flowing. Now since at transition or all the other time, this diode is connected parallel to this resistor. So that means whatever the voltage that we have got across this diode, the same voltage across the resistor. So now we know the voltage across the diode is minus 0.7 and which is connected to the resistor R2. So that means I can say VR2 equals to minus 0.7 volt. You see, this is the polarity plus minus. So now I want to determine, so I can say R2 is equal to VR2, I can say I2 R2 equals to minus 0.7 volt, and I2 can be expressed as, since it is series connection, I can be expressed as VI divided by R1 plus R2 times R2 minus 0.7 volt. So I can go further doing this. VI equals to minus 0.7 times R1 plus R2 divided by R2, which is minus 0.7 times 5 plus 2, 7 divided by 2. So that gives us minus 2.45 volt. So which means when the input signal is fluctuating between 10 volt to minus 10 volt, then we have a transition occurring through our diode. So that is our transition state voltage. So now we already learned from our from half-wave rectifier or full-wave rectifier circuit analysis that our next step would be to draw the transition state line. So we are going to draw the transition state line, which is, so roughly, let's say this is our transition state line, which is VI is equal to minus 2.45 volt. And we already learned that transition state line tells us the range of voltage, the range of input signal for which the diode is on, and the range of input signal for which the diode is off. So the question is, for which range the diode is on, and for which range the diode is off. So that we already learned that if the diode appears to be in anti-clockwise direction, if you keep our DC signal or the signal to my left, if the diode appears to be anti-clockwise direction, in that case, the value of the signal below the dotted line or below the transition state line, diode will be on. So diode will be on. And the diode will be off. So I can write VI greater than equal to minus 2.45 volt diode is off. And then Vi less than minus 2.45 volt, diode is on. So this way we have found out the range of voltage for which the diode is on and the diode is off. So next we're going to find out the time interval when the diode is on and when the diode is off. For that we did what? We found the intersection between the transition state voltage line and the signal. So for that, this is the intersection, and if we draw the vertical line here, which is intersecting the time axis. So let's say this is our T1 instant, this is our T2 instance. So clearly I can say from 0 to T1, so this interval diode is off. So because it is above the dotted line, so I can write T is greater than 0, less than equal to T1, which is, and T is greater than T2, less than capital T. In that case, all the value of the signal, you see, all the value of the signal is above the dotted lines. If you observe, so diode is off. On the other hand, between T1 to T2, on. So between T is greater than T1 and less than T2, diode is on. So this way we have found out the range of input voltage for which the diode is on and the range of input signal for which the diode is off. Also, the duration of time when the diode is off and the duration of time when the diode is on. So next we are going to find out the input-output relationship in the next unit.